All right, so, that's it. Here is the homework assignment, page 467, 5 through 13 odd, 25 through 29 odd. Not a whole lot of problems. Here's a summary sheet that I put together of all the information we've used. I don't know if this is useful or not. I just threw it together. I thought maybe that would sort of summarize everything. Basically, there's 5 types of integrals. The top limit is infinity. The bottom limit is negative infinity. There's a discontinuity on the lower limit. There's a discontinuity on the upper limit, or there's a discontinuity somewhere in between the two limits. Helpful, whatever. Maybe not. You can use it for something. Turn it over and use it for scratch paper or something. Okay, I did want to do some additional examples, especially some of the sort of little bit weirder ones in this domain. So for example, here's number 12 out of that homework selection. This one's pretty weird, so I thought this was worth looking at. Integral 2 to infinity of 3 over x squared minus x. It also draws together a lot of things that we've learned. So let's see how this goes. So this is going to be the limit as b approaches infinity of the integral from 2 to b of 3 over x squared minus x dx. Well, how am I going to do that integral? How am I going to do that? How would you do it? So one option is completing the square. I saw somebody do it that way. I don't recommend that. That's because it's really easy to do this, the denominator factors. So you can do this by parts. So this is equal to, we can write the parts, or not, I mean partial fractions, right? So we can break the fraction down. Since this is x times x minus 1, we can do a over x plus b over x minus 1. So we get the equation 3 equals a times x minus 1 plus b times x. So then let's see, 3 equals ax minus a plus bx. So there's no x's over here, so the a and the b, a plus b equals 0 is one equation. And there's only one constant, so it has to equal the 3, so a already equals negative 3, and then from here b equals 3. So that's like a super easy partial fractions. So then we're going to say we have our original integral, if the limit is b approaches infinity, of the integral from 2 to b of negative 3 over x, that's the a, plus 3 over x minus 1 dx. All right, and let's go ahead and do the antiderivative for that. So that's limit as b approaches infinity of negative 3 ln. All right, it's really absolute value of x, but my x's here are all positive. So based on that, I can drop the absolute value, right? From 2 to infinity, all those values are positive. So I'm going to drop the absolute values on this. I have a good reason for doing that, so I can do it. And this is from 2 to b. All right, now, if you try to do this limit by just plugging the top and the bottom as it is, you're going to have trouble evaluating it because this one's going to go to negative infinity and this one's going to go to positive infinity. So how am I going to know how, it looks like it's going to be undefined because I can't do, I can do infinity minus a finite number and get infinity. But if I'm comparing two infinities, I don't know which infinity is sort of going to win out there. So what I can do is rewrite this using log rules. That's kind of what you have to do this. So I'm also going to factor out the 3 at the same time. Just make it a little clearer. Limit b approaches infinity. And then the next thing I'm going to do is I'm going to say, this is ln of x minus 1 minus ln of x. So I can write that as the quotient ln of x minus 1 over x. Now, for some reason, I threw the absolute value back in there. I don't know why I did that. And that's from 2 to b. All right. So then, this is equal to 3 times the limit as b approaches infinity of ln of b minus 1 over b. Oh, that's interesting. Okay. And then minus, now when I put in the 2, I get ln of 1 over ln of 2. Should I write that? Sure, why not? ln of 1/2. It's ln of 1/2, right? ln of 1/2. Okay, so now I need to do this, these limits. All right, so I have 3 times. So let's look at this limit first. So let's split up the limit because this one's a constant. So I have 3 times, I'm going to put this, the limit as b approaches infinity of ln of b minus 1 over b minus, and then this is just ln of 1/2. All right, so I only have to worry about the limit of this part. So this is a little bit tricky, so let's pull it aside and sort of look at what is the limit as b approaches infinity of the ln of b minus 1 over b. So we have to really sort of work at that limit a little bit. So one thing is that if I have a limit of a continuous function, I can put the limit inside that continuous function. So then I'm going to have ln of the limit as b approaches infinity of b minus 1 over b. Well, what's the limit as b approaches infinity of b minus 1 over b? Well, this is a rational function. The coefficient of the top and bottom are equal, so I do ratio of coefficients. So this limit is 1, and I have ln of 1, which equals 0. So all that work tells me that the limit as b approaches infinity of ln of b minus 1 over b is 0. A slightly easier way to think that out without writing it out is, as b approaches infinity, this is a rational function. It's going to 1, so ln of 1 is 0, and so that's 0. So you can do that a little easier. Okay, and then I have minus ln of 1/2. And so that equals negative 3 ln of 1/2. All right, now, if you have a nifty calculator like this one, you can just put into it the integral from 2 to infinity of 3 over x squared minus x. And it tells you the result is 3 ln 2. 3 ln of 2. All right? So did I get it wrong? No, because this is equal to 3 times negative ln of 1/2, which is equal to, I can put the negative 1 up as an exponent, 3 times ln of 1/2 to the negative 1 power, and 1/2 to the negative 1 power is 2, so it's 3 ln 2. So I got an answer that looked like this, but because we understand log properties, we know that's the same as this. That was a little bit tricky. But I think that this whole thing was a little tricky because you really can't evaluate this limit without using the log property here. Okay, so there you go. There's that one. We'll look at a couple other examples.